Now the unstable atmosphere. Suppose that we send a radio sende, and radio sende send back the temperature above the earth, and once again we determine the atmosphere stability by comparing the environmental lapse rate to the moist and dry adiabatic rates. In this case, the left picture is showing the environmental lapse rate is 1.5 degree per 100 meter. So a rising parcel of unsaturated surface air will cool at the dry adiabatic rate, because the dry adiabatic rate is less than the environmental lapse rate. The parcel will be warmer than the surrounding air and will continue to rise, constantly moving upward away from its original position. The atmosphere is really unstable. Of course, a parcel of saturated air cooling at the lower moist adiabatic rate will be even warmer than the air around it. In both cases, the air parcel, once they start to going upward, will continue to rise on their own, because the rising air parcel are warmer and the less dense than the air around them. The atmosphere in this example, we would say, is absolutely unstable. And air parcel in an unstable atmosphere, it is being warmer and less dense than its surrounding environment, and also has an upward direction force, it's called buoyant force, acting on it. The warmer the air parcel compared to the surrounding, the greater the buoyant force is, and more rapidly the air parcel will rise. So we can conclude that the absolute instability result, also the absolute instability occur when the environmental lapse rate is greater than the dry adiabatic lapse rate. So far we have seen that atmosphere is absolutely stable when the environmental lapse rate is less than the moist adiabatic lapse rate, and absolutely unstable atmosphere we find when the environmental lapse rate is greater than the dry adiabatic lapse rate. And the one thing in this slide I would like you to draw your attention that there are three lines here. This one is gamma M, moisture, that's been saturated condition. This gamma D is unsaturated parcel, and gamma E is environmental lapse rate, and gamma D is dry adiabatic lapse rate. So in this chart, the atmosphere is completely unstable, absolutely unstable, because the environmental lapse rate is greater than both dry adiabatic lapse rate and moist adiabatic lapse rate. But one thing you may be confused with this line, that you have to look at here. From here to 1 kilometer, something like that here. So this one is intersecting somewhere here. That's been 1 kilometer here. So this one is going down from, I would say, 20 to minus 10 degree, that's been 30 degree. So this is the rate. So this rate is higher. Again, you are going this one for dry adiabatic lapse rate from 20 to 0 degree. That's mean you are climbing 2 kilometers over here. So your temperature is dropping off 20 to 0 degree, that's been 20 degree. So 20 divided by 2 is 10, so 10 degree per kilometer. Okay, so this is why those lines, this is high rate, this is less than this one. So this is the way you have to look at those graphs.